Okay, so this is question number 1C from test 3 of Physics 2, and we're asked to figure out the potential difference between points A and B, ending at point A. We're also given this battery of 1.5 volts of EMF, and the segments A to B, 0.22 meters, B to C is 0.22 meters, and then this length is also 0.22 meters, and that follows across the entire circuit. So the way that we're going to approach this problem is the first thing we're going to do is recognize that the current, we're going to use the equation that current is equal to charge times the electron density times the area, cross-sectional area, times the electron mobility, times the electric field in the wire. And normally, if these wires were different sizes and of different characteristics, we would have to solve for E in terms of all of them and their different characteristics. But in this case, they're all similar, so we can just go directly to say that I will be proportional to E. So the first thing we're going to want to try and do is use the node rule, because it's the easier one. And so we're going to say, we're going to label our paths here. This is path 1, path 2, path 3, path 4, path 5, and this middle one will be path 6. Okay, and we're going to just walk around the circuit here. Path 1 is going to go from A to B, and at B, the electric field of 1 is split into two electric fields, E2, and that is in addition to E6, because it's going there and there. In the same way, we're going to start at E4 here, and we're going to say that at this node here, we have E4 and E6 coming together, and adding E4 plus E6 will get us to E5. We're also going to notice that the electric field at these three locations, 2, 3, and 4, are all equal because of these node rules that we've already come up with, and due to the fact that the current flowing through there will be the same for all of those. And the current flowing through here and here must be the same as well due to the conservation of current. Alright, following this, we can now move on to the loop rule, and we're going to start by doing the loop rule for this small loop here. And if you remember the loop rule, you know you have to include your EMF. Oops. And you know that the EMF is minus your change in voltage, which we know change in voltage also is equal to electric field times length. And what we're going to say here is that length is equal to 0.22 meters. And so we're going to say length times E1, because that's how far we're going, plus this next length times E6, plus this next length times E5, and that is the total potential difference that is, I guess, traversed over this path, and eventually that should all equal 0 because potential difference adds to 0 in a closed loop. Now, using some of our conversion factors here, we can say, from the node rule equations, we can say that EMF minus L is equal to 2E1 plus E6, and that just comes from the fact that E1 is equal to E5, so we switch those. And then we also can say even further that EMF minus L 3E1 minus E2, and that's just going another step, substituting the fact that E6 is equal to E1 minus E2. So that is the loop for this left loop. Now we're going to move on a little bit and we're going to look at the loop for the entire thing. So you can see this entire thing here is what we're going to try to be looping around. And that, using the same type of logic, we're going to say EMF minus L, because L is our 0.22. And again, we're going to start with E1, because that's where it starts. Then we're going to continue on with E2. Continue on with E3. And likewise around the thing for 4 and 5. Okay, so that's where we are right now. And using some more conversion factors, we're going to try and get it in terms of just E1 and E2 again, because that will make our life simpler. And since we'll have 2 equations, we can, and 3 unknowns, we can put 1 unknown in terms of one of the other unknowns. So we're going to put L, and then 2E1 plus 3E2. And that just comes from using these node rule equations similar to the way we did it down here. Okay, and that's all going to equal 0 as well. Sorry, I haven't been doing that. Alright, now that we know this is equal to 0, we know this is equal to 0, so we can set them equal to each other. So combining these two, we can say that, and crossing out the L's and getting rid of the EMFs, we know that 3E1 minus E2 equals 2E1 plus 3E2. And doing a little quick math here, we're going to put the things on each side. 3E1 minus 2E1 equals 3E2 plus E2. And you're going to say E1 is equal to 4E2. And giving that a little easier, we can put E2 is equal to 1 over 4E1. Okay. Now at this point, we're going to go back in and substitute this 1 over 4E1 into E2 in the very first equation that we derived for the small loop here. So I'm just going to move this down a little bit. And we're going to say that EMF, this is going to be substitution step. And we're going to say EMF minus L times 3E1 minus 1 over 4E1 equals to 0. Alright, now we can actually, simplify this down to all variables that we know. And we can say, very simply, 2.75 LE1, that just comes from 3 minus 1.4. Move that over to the other side. LE1. And then eventually all that we're solving for here is E1, because that is what's going to help us eventually determine the change in potential. Alright, finally, okay, so now we have E1, and we know that the change in voltage is equal to the electric field times the distance. And what we're looking for, if you remember, is we're looking for the change in potential from this point to this point. And we know the electric field at this point, and we also know the length at this point. So simply multiplying these two values together, we should be able to get the change in potential or change in potential difference. And formally, you can write it out like this. But it's kind of a hassle, but I'm doing it anyway. E1.L, just like I said. And substituting in what we know right here for E1, we can say EMF over 2.75 L. And then we know L is just L. We cross those out. And the EMF we know is 1.5. We got that from the problem statement. So we can just say that 1.5 V over 2.75 is equal to 0.545 volts. That's in volts because it's potential difference. And we also noticed that it's positive, and that's because we're trying to find what happens when you go from B to A, and we noticed that we're going from a more negative state of charge to a more positive state of charge, and that's why the answer is positive. Alright, hope you enjoy it. Thank you. Bye.